Hello, and welcome to the equation to graph tangent parent function video. This is going to be really similar to the previous videos that we just watched where I went through and talked about the parent function and the features of sine and cosine, but now we're just doing it with tangent because tangent looks just a little bit different. So let's see if we can go through. I'm just going to remind you really quick that when I'm talking about features of trig functions, which I'll write up here, when I'm talking about features of trig functions, I'm talking about domain, I'm talking about range, talking about the period, which we covered in previous videos as well as in class today. I'm talking about the x-intercept. I'm also talking about asymptotes and amplitudes, if it's applicable. So in our, again, last videos talking about sine and cosine, sine and cosine have amplitudes, but they did not have asymptotes, so we didn't really talk about those. Today, it's the reverse. Tangent, or any other functions besides sine and cosine, don't have amplitudes, but they do have asymptotes. So let's get into that. So if I was to graph all of this, let's say we'll have f of theta is equal to tangent of theta. I'm going to do what I did in the previous videos. I'm going to pause again and set up kind of all of my features and my scaling. So I'm going to pause. Feel free to pause right afterwards to write all of it down. So here we are. You can see I've zoomed in a little bit. Feel free to pause to write down everything. You'll be able to see that for the graph, I'm using the exact same scales as I did in my previous videos. So the the y-axis is by 1, and the x-axis is by pi over 4, but I'm only marking up every pi over 2. I have all the same features: domain, range, period, amplitude, asymptote, x-intercept. I do want you to note, however, I'm leaving an extra space here between domain and range, and also an extra space between asymptote and x-intercept. That is intentional. You might want to give yourself a little extra room for those, as well as x-intercept, because we know that can be a little bit interesting. And then lastly, over here, I have built a parent table for us. This parent table is slightly different than our others because last time we were going from negative pi to positive pi. Here we're going from negative pi over 2 to positive pi over 2, and that's because tangent has a smaller or shorter period. Now remember, a period is however long it takes a function to repeat itself. Now for sine and cosine, that was one full rotation around the circle, but for tangent, it is in fact shorter. So let's get into that. And let's just start at 0. So remember, all of these radians here, those are on our unit circle, and we are asking what is the tangent value of those. Quick reminder, tangent is our y value over our x value, or sine over cosine. So if you'd like to have your sine and cosine graphs out while you're working on this, that does make perfect sense. So let's take a look at where we are at. So let's see, I think I'm going to do these in blue. So if we're looking at 0, well, 0 right here, that's sine over cosine. That's our y value of 0 over our cosine value of 1. 0 over 1, that's just 0, okay? That goes right there. Now, as we can see, it's asking us for pi over 4. So let's check next at pi over 4. So at pi over 4, that coordinate is square root of 2 divided by 2 over and square root of 2 over 2. Now, anything divided by itself is going to be 1. So the y value divided by the x value there is going to just give us 1. Now, if we take a look at pi over 2, the coordinate there is 0, 1. So it's our y value over our x value. 1 over 0. Oh no, 1 over 0, you're not supposed to have that. That's something that's not going to work. You can't divide by 0. So in this case, this is going to provide us with an asymptote. So anywhere where you get that undefined, that's going to give us an asymptote there, or anywhere where we are dividing by 0. So let's keep going until we get to 2 pi, and we might be able to see a pattern starting up. So let's next head to 3 pi over 4. Well, 3 pi over 4, the only difference there between 3 pi over 4 and pi over 4 is that now the x value is negative. So it's positive square root of 2 over 2 divided by negative square root of 2 over 2. Anything divided by itself is 1. The only difference here is that now that's going to be a negative 1. So that's going to be down here. Let's see at pi, we can see, all right, coordinate there is -1, 0. So 0 divided by -1, that's still just going to be 0. Okay, let's mark that in. Let's take a look at 5 pi over 4. So 5 pi over 4 right here. Now, both our x and our y value are negative. Negative divided by negative is a positive. Square root of 2 over 2 divided by square root over 2 over 2. Ooh, that's hard to say really fast. Still going to be 1. So now we have another positive 1. And at 3 pi over 2, this is the point 0, -1. -1, our y value divided by 0, our x value, not going to work for us, can't divide by 0. So we're going to have, an asymptote. And so you might be able to see where that repeating pattern is happening. So I can see that I have a few points, an asymptote, 3 points, an asymptote. Let's see if that continues over here. There we go. So for, 7 pi over 4, that's in our quadrant 4, now the y value is negative. So we have negative square root of 2 over 2 divided by a positive square root of 2 over 2. Negative divided by a positive is in fact negative. So this is going to give us a value of -1. And then 2 pi right here, that's going to give us the same value as 0, which in this case was also 0. So we're starting with that same type of pattern. Now, when we connect all of these together, it's going to actually kind of look like a quadratic, or pardon me, not a quadratic, a cubic function. It kind of goes off there. Now we only see the first half of that one, but let's go backwards. Let's see if we can re-engineer. Well, over here, negative pi over 4, that's going to be the same as 7 pi over 4, so that's going to be at -1. And negative pi over 2, that's the same as 3 pi over 2. Those are, in fact, coterminal angles. So that's going to give me an asymptote. I can fill out the rest of the graph there. So we can see that we're, again, continually having this cubic-looking type function. And if we were to continue from here with all of our coterminal angles, at -3 pi over 4, it's going to be the same as 5 pi over 4. It's going to be at 1. Negative pi is the same as pi. So it's going to be at 0. What would be -5 pi over 4 is the same as 3 pi over 4. So that's at -1. -3 pi over 2 is the same as 1/2, so that's going to bring me one of my asymptotes. And as you continue forward, you may just continue with the pattern. You may not actually be looking at the coterminal angles anymore, and that's okay. I'm just going to finish up here real quick. -7 pi over 4 is the same as pi over 4, so that's going to be 1. -2 pi is the same as 2 pi or 0, which was 0. So when I graph the rest of these, again, we get a cubic-looking function. Feel free to take a look at this on Desmos, just type in tangent of x or theta, and see what happens. But this is kind of what our function looks like. So we repeat ourselves in a much shorter interval, or again, period. And you can look at that period from asymptote to asymptote if you want, if that's kind of what you want to use as your boundary, so the distance between pi over 2 and 3 pi over 2. Or if you look from here to here where we have our x-intercepts when they start to repeat, that's 0 to pi. So if we come back and we take a look over here at our features, our period, we already mentioned that was pi. I've said previously that our amplitude, there is no amplitude. There may be a vertical stretch of short, but the actual vocabulary word of amplitude we're only going to be using for sine or cosine. So it's going to be NA. And then for our range, we got arrows going up and down forever and ever, so that's just going to be -infinity to +infinity. So now we have 3 features left: our domain, our asymptote, and our x-intercepts. And this is where things get really interesting. So I'm going to start with the x-intercept first, do the asymptote, and then the domain, because those are going to stay really connected. So the x-intercept, as I've mentioned earlier, you can look here. So we just have to pick one. I'm going to pick the one at pi right here. So parenthesis pi, but we don't just have one x-intercept. We have a bunch of x-intercepts, and they are all a distance of pi apart. So I'm going to pick my x-intercept of pi plus pi, but I don't just want to add it once. I want to add it or subtract it as many times as I want. So I'm going to say pi n, where n is an element of the integer, so it can be positive or negative. So I'm picking my starting x-intercept here of pi, and I'm going forwards and backwards pi n number of times, as many times as I want. And then again, this is a point, so I'm going to do comma 0, because that is my x-intercept. There we are. Little points everywhere. Okay, so that's what we have for our x-intercepts. We're going to do something really, really similar with our asymptotes, but instead of writing it as a point, we're just going to write that as x is equal to. So we'll have x is equal to, let's pick an asymptote. You can really pick any asymptote that you want. I'm going to pick pi over 2 just because it's the first positive asymptote that we have. So I'm going to pick my asymptote of pi over 2. And I see, okay, my asymptotes are pi apart. So I'm going to say plus pi. But I don't just want to add pi once. I want to add or subtract pi an n number of times, as many times as I want, where n is an element of the integers. So these are my asymptotes. My asymptotes are written really similarly to my x-intercepts. Again, only difference, I'm not writing it as a point, I'm writing it as x equals. So I have, starting at pi over 2, an asymptote every pi in either direction. Now, when we take a look at our domain is all of our possible x values that we can have. So our domain is really almost all the x values. It's really negative infinity to positive infinity. The only time where we can't have that x value is at the asymptote. So it's going to be from negative infinity to positive infinity, colon, except x cannot be equal to our asymptotes. So pi over 2 plus pi n, where n is an element of the integers. So when you're dealing with tangent, find your asymptote first, and that's just going to help you with your domain. Your domain is going to be negative infinity to positive infinity, except whenever you have those asymptotes. So if it helps you to maybe like highlight a little bit, like here and here, are really the same thing. Only difference is that asymptote is when x is this thing. Domain is saying, hey, x does not happen at that thing, if that makes a little bit more sense. So those are all the features that we have. Lastly, I want to take a look at this table, which we can see right here. We actually have, again, asymptotes at negative pi over 2 and pi over 2. So we're just going to write those as undefined. You can write the full word undefined, or you can just write UNDEF. So that's for undefined. And then for our other points, we have -1, 0, and 1. And this is what you're going to have for your parent function. And this is what we'll be using when we look at our transformations in the very next video. Let me know if you have any questions. I look forward to seeing you soon.